let's continue talking about sequences, and then today I aim to start talking about series. So as we were saying last time, a sequence can be increasing or decreasing or neither. Right, and remember, increasing means an plus 1 is greater than an for all n. Right, each one, the next one is always bigger than the one that came before. That's what increasing means. Decreasing is the opposite. An plus 1 is less than an for all n. All right, that's decreasing. And we talked last time about we did some examples of showing that a particular sequence is either increasing or decreasing. You'll have some more of those on the homework to try. And then the other word that I said was monotonic. Monotonic. This means it's just either increasing or decreasing. And of course, there are many sequences which are neither, right? It could be, a given sequence could be increasing, or it could be decreasing, or it could be something else. Neither of those two things. So here's an example: minus n to the n. This is not increasing or decreasing. This is not monotonic. Actually, if this is your job on the homework to, show that this is not monotonic, actually this is quite easy. It's much easier than proving that the sequence is increasing or proving that it's decreasing. To prove it's not monotonic, you can just write out some terms. So the first term, the terms are, the term n equals 1 will say minus 1 to the 1, right? The term n equals 2 will say minus 2 to the 2. The next one would say minus 3 to the 3, etc. I think actually these are all the ones I'm going to need to write out. If I were to just calculate each of those, that's negative 1 first, and then this is 4. Negative 2 squared is 4. And then negative 3 cubed. 3 cubed is 27, but it's negative 3 cubed, so it's going to be negative 27, etc. And now, this, you can see, it is not increasing every time, and it also is not decreasing every time. All right, so this, can I say, it goes, up and down, right? Like, the second one is bigger than the first one, but the next one is lesser than the second one, right? So, in this step, it increased. In this step, it decreased. That means that this sequence does not always increase, and it also does not always decrease. So it goes up and down, so it's not increasing or decreasing as a sequence, right? I was being fairly dismissive of this kind of argument last time. I said if you want to show something is increasing, it's not enough to just write out a few terms and then say, look, see, it's increasing. This actually, it is good enough to argue in this way. If you want to explain why it is not increasing, all you have to do is demonstrate one particular step in which it's not increasing. So actually, it is good enough to say it's not increasing. Look at this, it went from 4 to negative 27. So it's not increasing for that reason. And it's also not decreasing for this reason, because this one went minus 1 to 4, and that's not decreasing. So to show that it is increasing, you have to prove something using the definition, which is fairly involved. To show it's not increasing, much easier. You just find some specific terms where it didn't increase. All right? So that one is not monotonic. All right? One other property that sequences can have or not is some sequences are bounded. And this probably means what you think it means. Bounded means it doesn't get super big. Like it has a certain limit as far as how big the terms can be. And so the way that I'm going to write that is this. If you like, you could write this as a definition. If there is some number, I'll say big M. Big M is going to be the bound. If there's some big M with an less than big M for every n, that means some big number so that everything in the sequence is always less than this big number, all right? Then that number is called an upper bound for the sequence. Then this number, big M, is called an upper bound for the sequence an, and an is called bounded above. All right. If there's some big number where all the terms are less than that number, then we say the sequence is bounded above, and that number is called an upper bound. All right, and the picture you should have in mind for this, you can draw the plot of a sequence. It doesn't look like a curve, but it just looks like a bunch of dots. The idea is if you really have some m like up here, so that the terms of the sequence are always less than that. They might get kind of close, but they always stay below the line. That's what bounded above means. The terms never go up past m, right? And similarly, there's something called bounded below, and it means all the same stuff. It means there's some line like down here so that the dots are always above the line. So I'm going to write that business too. For that, in our book, they use a little m for the lower bound. So if there is, I'm going to say all the same stuff, it's just the inequality will be the other way around. If there is some little m with an greater than little m for every n, then the little m is called, I'm trying to write exactly the same stuff, a lower bound for the sequence an, and we say an is called bounded below. All right, and the picture for that is similar to that picture that I drew there. It's just that the sort of dotted line will be at the bottom this time. So the picture that you should have in mind for a sequence which is bounded below is you have some perhaps big negative number, and then all the terms are up here. I don't know where they go. I'm just trying to, right? This is the picture that you should have in mind when something is bounded below. All right, and if a sequence is both of these, bounded both above and below, then we call it bounded. So if it just says bounded, that means above and below. So this is the end of my lengthy definition here. If an is bounded above and below, then it's called just straight up bounded. And the picture you should have in mind for this is there's sort of like, there's this upper bound, and at the same time there's also a lower bound, and all the dots are stuck in between these two. They might go back and forth, or they could just like approach one of them or something. But this is the picture you should have in mind for a sequence which is bounded. It's got something up here where the dots never go above, and also something down here where they never go below. All right, this is a bounded sequence, what it looks like. I hope these are fairly like ordinary terminology that everybody is fairly comfortable with. Just some quick example here. How about an equals 3 to the n? Is it bounded above? Is it bounded below? And if so, by what? 3 to the power n. So you want to think about what this looks like when you plug in various values of n. Anybody want to say, is this one bounded above? I see some people shaking the heads. Yeah, I agree. If you think about what the plot of this would look like, 3 to the n, you start at 3, I suppose, right? And then the next one would go all the way up to 9. Actually, these terms just get super big immediately, and they continue to increase forever, right? This one is not bounded above because there is no single number which is always bigger than 3 to the n for every value of n. All right, so this is not bounded above. All right, because 3 to the n, if n is big enough, that will grow higher than any specific upper bound that you could think of. What about, is it bounded below? I think it is bounded below. Can anyone tell me, like, if it's bounded below, what's a lower bound? Do you have something in mind? 0 is a lower bound. Yeah, all of the dots are above y equals 0, right, on this plot. Actually, I would have also accepted 1 or 2 as the lower bounds. Or if you want to be silly, 2.8 is a lower bound, right? It's just any number less than 3 would count as a lower bound. So this one is not bounded above. It is bounded below. And he said, he might as well, m equals 0 is a lower bound because 3 to the n is always more than 0. But it's also, always more than 1 or 2. You could choose any number, really any number less than 3. 3 itself does not count as a lower bound because technically in the definition that I gave here, it has to be strictly greater. So 3 is, the first term is not greater than 3. So you can't use just straight up 3 as your lower bound. It has to be some number less than 3. All right, it could be negative a million if you want to, because it's less than 3. Great. How about, here's a fun one. How about an equals sine of n? This is very weird. Sin. This is the sine of n. Maybe I'll do that. What does the plot of this look like? The terms, they would be sine of 1, sine of 2, sine of 3. Anybody remember your sines and cosines? What is sine of 1 radian? The answer is no, I do not remember. A sine of 1 radian is like nothing. I mean, it is something, but you can plug that into your calculator. You will get an answer, but it's not any special number. And neither is any of the other ones, right? Sine of 2, sine of 3. I consider these, they are not, if you want to, you can plug these numbers into your calculator and you will see answers. But I would say, for all intents and purposes, these are all just basically like random numbers between -1 and 1, because sine of x, it has to be between -1 and 1. But I have no idea really what those values are. So if I were plotting them, this is not actually what the values look like, but I would expect them to look something like here's 1 and here's -1. It's just like you just get like various dots in this. The sine of 1, the sine of 2, the sine of 3. They're going to be something like that, right? Is this one bounded above? I think it is. Can you tell me an upper bound?
2.
2, yeah. Actually, 1 is also an upper bound here, just because the only values that actually hit 1 for sine would be multiples of pi over 2, and no multiple of pi over 2 can be written as a whole number like this. So, but I would accept 2 also. Really, it's upper bound. You could take anything up here and anything down here as the upper and lower bound. So this one, this is bounded. remember bounded, when I just say bounded, that means bounded above and also bounded below. And you could say an upper bound, I'm just going to go for it. Let's say an upper bound would be 1, right? Sine of a whole number can never equal 1. The only values where sine of something equals 1 are multiples of 2 pi. And a whole number is not a multiple of 2 pi radians. And then at a lower bound, we could take -1 for exactly the same reason. All the values of the sine are above that. All right, so sine of n is bounded. Strange but true. What about, here's another good example to keep in mind. -1 to the n. Maybe we can just talk this one through. Is this one bounded or not? You see the thumbs. Bounded? Not bounded. I see a few thumbs. I'll wait for the thumbs to roll in. Is it bounded? That means, bounded means there's something that's always, some number that's always greater than those, and also some number that's always less than those. Or if you think it's not bounded, it means that this maybe grows forever up or down or something like that. What do you say, bounded? Not bounded? I say bounded. I see the thumbs. Thank you for bringing the thumbs. Yes, this one is bounded. If you were to write out the terms, this is -1, 1, -1, 1, -1. And if I were to plot those, they just sort of go back and forth, but they do not grow up forever and they do not grow down forever. So this one is bounded. Above and below. What's an upper bound? I would say like 2 is an upper bound, and -2 is a lower bound, if you wanted to say it specifically. All right. This is a classic example of a bounded sequence. All right, this is what bounded means. I would like to say a few words about bounded and convergence. These are kind of related. So let's talk about boundedness versus convergence. If you think about this in a certain way, you might feel like these are kind of the same thing. They are not the same thing, but actually they are kind of closely related. For example, when I think of something which converges, like just think about what the picture looks like. Converges on a picture, I imagine something like you have a sequence which maybe it like grows, but eventually all the values end up being the same after a while, or they are approaching some particular common value, and often I might draw in a dotted line there. Like these, I'm trying to draw these terms so that they are approaching that dotted line, right? So this one, as I've drawn it, it does converge. It converges to the dotted line, and it is also bounded by the dotted line, bounded above, and is bounded below by just like, well, whatever you want. You can take a lower bound down here. The upper bound is a little bit more interesting. So this one is both bounded and convergent. Convergent, right? It converges and it's also bounded. Is that always the case? That's what I want to know. Like, do these two things always go together, or is it possible that you could have a something that converges but it's not bounded, or could you have a bounded but it's not convergent? Anybody have any ideas? Is it possible? Like let's just ask what I just said. Can we have bounded but not convergent? This would look like, that would mean you can actually, like if it's bounded, then you can put sort of dotted lines above and below, and all the dots have to be stuck in the middle. But does that automatically make it convergent? You got an idea?
I think like sine of n is an example of it being bounded but not convergent.
Yeah, sine of n is like this right here. It is the case that like all of these dots are forever stuck in between those two bounds, the upper bound and the lower bound, but it doesn't converge, right? They just bounce around forever. I had another example in mind, actually. Did you have another? Yeah, I think this one is even more obviously bounded, but it doesn't converge. This one, you might wonder if this. I mean, this one doesn't converge either. Although this one, pretty obviously to me, does not converge to any particular value. That's the standard example. Can we have bounded but not convergent? The answer is yes, because minus 1 to the n is bounded but does not converge. Diverges, right? That's the opposite of convergent. Minus 1 to the n is bounded but it diverges. All right, so you cannot have bounded. No, you can have bounded but not convergent. What about the other way around? Can we have convergent but not bounded? Convergent but not bounded. Any thoughts about that one? What I'm imagining on the picture, convergent means sort of, I don't know what happens at the beginning, but convergent means eventually when you go far enough, the values, maybe I'll draw one which converges to 0, right? Made a straight, wrecked it. I'm trying to make a straight line. This is going to be so worth it. Oh yeah. All right, so this is what it looks like for convergent. I'm making them converge to 0. It doesn't really matter what happens over here. This is converging. Some other stuff could happen. Is it possible for this to be unbounded? I see a mixture of noses and yeses. You may be concerned about, even if it sort of settles down here. So one thing I could say about unbounded, after this point, it can never go up to infinity, right? Because I said it's going to converge here, and that would mess up the convergence if it went up to infinity over here. What about over here? Anybody feel like maybe it could go up? Could it sort of do this? Maybe have an asymptote or something, and then eventually come back down. Is that possible for a sequence? I mean, we've never seen an example like that, but is that even possible at all? People seem less sure of themselves. I did a moment ago. Yeah?
This is like a different example, but isn't ln x not bounded but convergent?
Mm-hmm. Yeah. So this is an excellent thing to notice. This kind of a thing, which I'm trying to draw here, that definitely is possible if you're talking about a function. You can have, say, a continuous function which goes up forever and then comes back down and eventually converges, right? But it's not bounded because of this thing. That is possible with a continuous function. Can you do that with a sequence, though? The answer is no. Because if you just think about, how many, so I'm going to erase that. All those dots that I drew, that actually cannot happen if it's a sequence. Because I already told you, starting from here on, it's just going to be close to the 0 this whole time. What could it do before this? Well, actually, before that point, I didn't really say where that point is, but let's say, let's say this is term 100, all right? Could the first 99 terms go up to infinity? The answer is no, because there's only 99 of them. They can go up however high they go, but they don't go to infinity if there's only a certain amount of them, right? The only way that a continuous function is sort of allowed to go to infinity is because there's infinitely many points along that curve, and they really can go up forever. But it doesn't make sense for only 99 points here. You can't draw 99 points that go to infinity, because there's just one of them is going to be the biggest, and then that's the biggest it ever gets. It doesn't go any higher than that. So anyway, the answer to this question is no. And I will try to explain in some words why this is not possible. This little diagram here, those points that I drew don't actually go all the way up to infinity. They only go up to here, right? And you can't just squeeze in more points because there's only going to be so many of them. So I'll try to say it in this way. this is not possible. And why? This is not going to be a technical proof. But the idea is beyond, well, let me say it this way. If it converges to some value, let's say L is the number that it's converging to. L is the limit. All right. In my picture, L is 0, but it could be converging somewhere else. If it converges to some value L, this means that all terms past some point are super close to L. All right. How close exactly? Well, if you want to answer questions like how close exactly, you really have to go back to the technical definition of the limit in terms of that epsilon and that big N. That's really what I'm getting at here. But there is some point for which beyond that point, all the terms are super close to the limit. So that means beyond this point, all the terms past some point. So past that point, it's bounded. That's because all the terms are super close to L, so they don't go out to infinity or something like that. All right? What about before that point? It's also bounded before that point just because there's only finitely many points before you get wherever this is, right? And then those points, since there's only finitely many of them, there's just like some biggest one. They can't go up forever. All right? So past that point, it's, I meant to write bounded. I wrote bounds. It's bounded. All right? But before that point, we have only finitely many terms. So those are also bounded. Because if you want terms which go to infinity, you have to use infinitely many different terms to make that happen. You can't go to infinity with only like 7 terms, right? Because 1 out of those 7 will just be the biggest. Okay, this is a little technical, the idea that I'm getting at. So anyway, to summarize everything that I said here, it means that convergent implies bounded. This is how I would write this, sort of logically speaking. Any sequence which converges is automatically bounded, but not conversely. That is, it is not true that any bounded is automatically convergent, because we already saw like -1 to the n is bounded, but it's not convergent. All right? Convergent implies bounded, but not conversely. All right. Excellent. One last thing to say about this before we talk about series. There is one important case in which a bounded will automatically converge. So one important case in which any bounded also converges, and that is the case of monotonic sequences. So it turns out, and I'm going to write this as a theorem. This is an important theorem in the the mathematics of sequences and series, and it's so important it has a name. This is called the monotone convergence theorem. The monotone convergence theorem. It says if your sequence is bounded and monotonic, then it does automatically converge. So if an is bounded and monotonic, then it converges. All right? Just being bounded is not enough to converge, but if it's bounded and also monotonic, then it definitely must converge. And this, I don't want to do a proof of this. If you're interested, you should take real analysis. This is a math major course. But anyway, I want to talk about, this is actually easy to see on a picture. For example, bounded and monotonic. What does that look like? Well, here's a picture of, I'm going to draw a sequence. Let's draw a sequence which is increasing and also bounded. All right, so increasing and also bounded means, I'm just sort of making this up, but increasing means the dots just go up as you move to the right. Every one is a little bit higher, or perhaps a lot higher than the previous one. All right, so that's what increasing looks like. But what if it's bounded? So bounded also means there's some sort of horizontal guy like this. That's the upper bound. Now, if I continue drawing this sequence, what's going to happen if I continue drawing this sequence to the right? Remember, the sequence, I am trying to draw an increasing sequence. So this one is increasing and bounded above. What's going to happen with these dots? I mean, I'm just making this up, but as you continue drawing them, they have to go up every time. I think what's going to happen is they will converge, right? Because they have to go up every time, but they can't overshoot the M because it's bounded. And so they must, at some point, just sort of pile up and converge to the M, right? It's actually not true that they must converge to the M. They could, if you want, converge to something lower down. I mean, slightly lower than the M. Like this, as I drew it right there, they converge to the M. But you could also draw it something like the M's way up here. Sorry, my dotted lines. And I could make it so that they converge somewhere else, right? They could converge to a lower value than the upper bound, or they could converge all the way up to the upper bound. So increasing and bounded above must converge, right? It's because the dots have nowhere else to go. They have to be increasing, but they can't overshoot the M. And so they're going to have to sort of pile up on one another eventually. All right? And similarly, if it's decreasing and bounded below, the same thing happens. So this is a picture of a decreasing bounded below. That means I have a lower bound here. And if my terms are decreasing, they have to just kind of accumulate down here somewhere. All right, this is decreasing and bounded must converge. All right, and this is the idea of the monotone convergence sequence. If it's bounded and monotone, then it converges. Just bounded by itself is not good enough, but if it's also monotone, then it must converge. All right, the monotone convergence theorem. It's a good thing to know about. Any thoughts about that? All right, this is all about sequences. Really, the material that is going to be most interesting for us going forward is all about series. I am permanently annoyed that the plural of the word series is series. I think it makes more sense to say serieses, even though it sounds stupid. That's just the kind of guy I am. So, the end of talking about sequences. Let's talk about series. Plural, series. All right, let's talk about series. So, the difference, sequence and series are not synonyms. A sequence is a list of numbers one after another. A series is what we get when we add up all the terms in a sequence. This is a series. Since every sequence is just a list that goes on forever, that means that every series is an infinite sum, right? Because I'm adding up all the terms in a sequence, and a sequence has infinitely many individual terms in it. We're adding them all up. So every series looks like an infinite sum. So this is written for a sequence an. The series is written the sum. I mean, it's written the way you would expect. It's written like that. Sum n equals 1 to infinity of an. That is the sum of all the terms in the sequence. Or sometimes just like a sum, right? I mean, if you're, I should put an in there. The sum of an, right? Oftentimes we won't even write the little boundaries for the summation, just because if I'm trying to do a series, I'm always going to add all of the terms. And so the upper value is always infinity. And the lower value, we're always going to start n at 1. And so, often we will just write this without the little bounds. And what that means, it always means n equals 1 to infinity. All right? This is called the series of an. We've actually already seen one example like this. Back when we talked about improper integrals, I did a little argument about this. The sum of 1 over 2 to the n. This is 1/2 plus 1/4 plus 1/8 plus 1/16. And I don't know if you remember, but I imagined adding this up like according to areas. Like the first one, 1/2 is like half of the box. That's 1/2. But then if I add in 1/4, 1/4 actually fills in half of the remaining space here. And then if I add in 1/8, that fills in yet another half of the space which remains. And in fact, all of these things, you can fit them all into this little crack, right? Because each one that goes in is just going to fill half of the remaining space. That means all of these things fit into this box of area 1. So actually this, I will say, turns out the sum 1 over 2 to the n, actually that straight up equals 1. And this is something that we'll be able to prove fairly easily as a simple example, although we'll have to talk about methods specifically for doing that, but this is the idea. All right, so big question is, like, if I just give you a series, like this is a fairly special case, but what if it was 1 over 3 to the n? What would that add up to? It's not 1, it's something else. Or what about some other weirder thing on the inside here? How do you even figure out what it adds up to? This is the major question of most of what we're going to be talking about for series. One more fundamental question is, like, what does it actually mean? What does it mean to add infinitely many things together? Infinitely many terms. This is a good question to consider. Of course, like in real life, you can't really add up infinitely many numbers and get an answer. And so it is tempting to ask, like, is this just some like abstract nonsense that has nothing to do with reality? The answer is kind of, but not really. It's kind of like all of mathematics is abstract nonsense. Like, for example, there is no such thing as the number 2. Like, the number 2 is an abstract idea. The question that people should ask about abstract concepts like the number 2 is that abstract concept actually useful for understanding the world? And the answer is yes, it is useful to know what the number 2 represents, because you can use this concept all kinds of ways in your real life. And this is a similar thing that I would say. Like, I would say, of course, like in real life, you can't add together infinitely many things. In fact, in real life, you can't even like sit in the same room with infinitely many things. Like, there is no such thing as infinitely many things in real life. But is this something which is useful for things which actually do occur in real life? The answer is absolutely yes. Like, for instance, things like compounded interest or all kinds of things actually can be expressed in terms of infinite series. So it really is an important thing. Anyway, can we just discuss in our remaining 10 minutes, what does it actually mean to add together infinitely many things? I'm going to think of this kind of the way that we think of an improper integral. So this is the definition, or I'll write it in a few steps here. Given some sequence an, I'm going to consider, rather than considering the sum of all infinitely many of them, which is something that it's not clear what that even means, I'm going to define another sequence called S. And S1 is going to be the same as A1. S2 is going to be A1 plus A2. S3 is going to be A1 plus A2 plus A3. All right, so this is a new sequence which consists of adding up some of the terms, but not all of them, right? Just like the first few terms. So S3 means you add the first three. S4 means you add the first four terms. Right? If I wanted to write this in general, I would say something like Sn, generally speaking, is the sum up to term number n, right? And you could write that something like this: I equals 1 to n, ai, right? This is the sum. If I were to write it all out, it would say a1 plus a2, to an, right? This is the sum of the first n terms. And this Sn is a sequence. This is called the sequence of partial sums. Partial sums meaning, like, what I'm really after is the sum of everything, but that's a little complicated to even think about. It is not so complicated to think about just taking only some of them up to a certain point. Those are called partial sums. They are not the entire sum. They are only part of the sums. All right? This is called the sequence of partial sums. And then, how do we define? Now S is a sequence, right? S itself is not a series. It's just a sequence of numbers. And now here's the real definition. The series sum an is defined as the sum, maybe I'll write it all out, n equals 1 to infinity, an equals lim n goes to infinity, Sn. This is the definition of what we mean when we say add up all the terms, all infinitely many terms. We mean you consider these partial sums, which only go so far, but then you take a limit as n goes to infinity of that sequence over here, all right? And this is something that we already know how to discuss, because that's the limit of a sequence, which is what we've been talking about for the past couple days. All right, this is another way to write this, although this is a little more confusing. Well, I don't know if it's more confusing or not. This is a1 plus a2 plus etc. down to an, right? You take only the first few terms on the beginning, but then you take the limit as the amount of terms you're taking goes to infinity. And that's how we define the series, all right? Because it is a lim of something or other, this may converge or it may diverge. That's because it's a lim of something, right? And we all know when you do a lim of any sequence, it might converge or it might diverge. So that actually is another big question that we're going to be talking about. Sometimes our series are going to be too complicated to actually calculate the answer, the value, but we can still say a lot about which ones converge versus which ones diverge, right? Let's talk about, I got two quick examples here, and these ones you can share with your friends on the playground. So these are two cute examples. The first one is not all that interesting to the kids on the playground, in my opinion. The second one is maybe a little bit more interesting. How about I tell you the sequence, and then we'll try to figure out what is the value of the series. How about an equals 1? This is one of the simplest sequences you can think of. All right? Just 1. I mean, no matter what the n is, the term value is 1. So that means if I were to write out the terms, it would just be like this. 1, 1, 1, 1, 1, etc. All right? Okay, What is the series? Then your job, find the sum an. N equals 1 to infinity, right? If you were to write out the terms of this sum, it would be 1 plus 1 plus 1 plus 1, etc. It's typical playground talk. Stoner talk. Yeah, man, like what if you just like add 1 over and over again? What are you going to get, man? The answer is it diverges. This is not a surprise, I hope. You cannot just add 1 over and over and forever and get a real answer. But can we just verify that this actually diverges? How do we do it? The definition of this sum is in terms, the definition of the series is in terms of the partial sums. So S1 would be just 1. S2 means you add up the first 2. S3 means you add up the first 3. S4 means you add up the first 4, and so on. Right? Can we actually add them? Yes, these are easy to add. I get 1 the first time, 2 the second time, 3 the third time, 4 the fourth time. I ask you, do you see the pattern? Sn equals, can anybody say a formula in general here? This is not a trick question. It's a fairly simple formula. What do you think? Sn equals n. Yeah, right. S1 is 1, S2 is 2, S3 is 3, S4 is 4. So yeah, generally speaking, Sn equals n. All right? And so we can find the value of the series. The series an, remember, is defined to be the lim of the Sn. But I have a formula for Sn here. It is n. So this is going to say lim n goes to infinity of n. And the answer is, well, infinity, or it diverges. Right? To no one's surprise, if you add 1 plus 1 plus 1 forever, it doesn't actually add up to something, it diverges. All right? I had one more, although I'm not sure we have enough time. Maybe I'll just tell you. This is a more interesting playground or stoner conversation. I've never been a stoner, but I did talk about math on the playground. This tells you something about my childhood and my present, let's be honest. I don't really talk about math at the playground presently. But anyway, here's a more interesting example. How about an, and we'll start off next time like this. Minus 1 to the n. Talk to your friends about this. Of course, the terms here, it's minus 1, 1, minus 1, 1, minus, right? It's like, yeah, man, what if I add these together one at a time forever? What does it add up to 0 or a half? I don't know. This is the question. What do you actually get if you try to, or maybe diverges? So that seems a little weird to me. But think about it. Ponder. We'll do this at the beginning next time after the quiz.